what we will do in this class is try to derive a circuit which can be used as a converter. So, we saw some devices, diode, thyristor and controllable devices. So, we will try to use a thyristor and see how we can get a converter using thyristors, and of course, since there is thyristor, there is some amount of control. Okay. Now, the simplest converter one can think of is a circuit like this. I have a thyristor. Now, suppose I connect a sinusoidal voltage source. Now, this itself acts as a converter where I have distinguishable AC and DC sides. Suppose I take the voltage across these two terminals as VD, V for instantaneous voltage, the subscript D stands for DC, and these two terminals, which are the terminals of the AC voltage source, are actually the terminals of the AC side. So, let me call this instantaneous AC side voltage as EM. So, M subscript M stands for maximum, cos omega OT. T is time, omega O is the angular frequency. So, it's in radian per second. So, if I have the frequency as 50 hertz, then it is 100 pi radian per second. Okay. So, there is a distinguishable AC and DC side. So, the converter is just one thyristor, and what I have is a AC side, a source which is having an instantaneous voltage Em cos omega OT, and a DC side is Vd. Now, we are more familiar with a DC voltage which is constant as a function of time. Now, for the purpose of this course, a DC voltage is a voltage whose average value is non-zero. So, I will repeat, a DC voltage is a voltage whose average value is non-zero. So, when I say DC voltage or DC side voltage, what I mean is an voltage with non-zero average value. Of course, the AC side is a sinusoidal waveform, so average value is 0. Okay. So, that is the definition of DC voltage that we will be following this course. The same thing is applicable even for the DC current. So, when you take the DC side current, I mean it is not necessarily a constant value as time progresses, but it is something with which is of course periodic, and we will have a non-zero average value. But if you look at this DC side voltage, what will be the DC side voltage? It depends on the instant at which you turn on the device. Suppose I turn on the device as if it is a diode. That means, suppose it gate current is always given, continuously given, then the thyristor acts as a diode. So, what will be the waveform? So, if I try to plot the instantaneous DC side voltage Vd as a function of time, then I will not try to mark the values on the abscissa. If I just look at the waveform to assuming that there is a resistor across the DC side terminals for simplicity, it will have a waveform which is sinusoidal for one half cycle and 0 for the other half cycle, and again sinusoidal. So, what I get is a DC voltage, but it is nowhere close to what is desirable. Now, what is desirable is the one that I have shown above. I mean I need a constant DC voltage, but I will not be able to get the constant voltage, but I should make it as close to the desired value as possible. So, how to alter this circuit of the converter in order to get a better DC side voltage? So, what we do is, let me try to get a slightly different circuit which gives a slightly better waveform. Suppose I take, instead of one thyristor, I take two thyristors, and of course, two voltage sources. So, let me call this instantaneous voltage across this voltage source as Em cos omega o t. Suppose this is Em cos omega o t plus a certain phase angle. I will talk about this phase angle shortly. Now, let me call this voltage across these two terminals as V d, which is our DC side voltage. Now, the question is, what should be this phi? What should be this phi? What is an obvious choice for phi? Suppose this first voltage is Em cos omega o t. What is the obvious choice for the second voltage that I have here? So, it should be shifted by 180 degrees. Now, my intention is I should get some sort of symmetry in the DC side voltage. So, if phi is pi, so instead of phi, if I make it say pi, that is 180 degrees. And if I give say for example, for this, just for the sake of simplifying our analysis, assume that the gate current is constantly given, then I get a waveform which is sinusoidal 0 say pi. Okay, I will try not mark this one. So, what I am trying to say is each of these durations are of pi radian. So, this is pi radian, this is pi radian, this is pi radian. So, here the abscissa is omega o t. So, what I have plotted here is V d. Now, compare this V d with the previous V d. So, the previous V d was something like this. So, which is better? I mean, without any mathematical analysis, which appears to be better just by looking at the waveform? The one with two thyristors instead of one thyristor. Now, there is some way of mathematically showing that one is better than the other. So, one can try to find out what is the harmonic content. See, what is desired is only DC, the rest are harmonic components. So, one can show that the harmonic component compared to the DC is much smaller in the second circuit compared with what is there in the first circuit. Now, can we further improve upon this? So, yeah, what is our goal? Our goal is to get a constant DC. If that is not possible, at least get close to a constant DC voltage. Now, why we started with the simplest waveform? This is the most obvious circuit. See, we started with simple circuit of one voltage source and one thyristor because it is the most obvious one. Okay. The next obvious circuit is adding one more such circuit in parallel. So, if I want to improve upon this, what one can do is I can try to add many such circuits in parallel. So, the intention is to get close to a constant DC voltage, but you will never get a constant DC voltage, you will only get close to that. So, we will see what are known as pulsations. So, you will see that there are pulsations in the DC side voltage. So, if you look at this, there are two pulsations per one cycle of the AC side voltage. Okay. So, we will define what is known as a pulse number. So, pulse number which is denoted by lowercase p. So, this pulse number is defined for a converter. So, pulse number of a converter is defined as number of pulsations cycles or cycles of ripple. So, I presume you are familiar with these terms, pulsations, ripple, the number of ripples that we get. So, it is number of pulsations of the DC voltage per cycle of the AC voltage. So, we see that in this case the pulse number happens to be 2, because if you look at one cycle of the AC voltage, there are 2 pulsations of the DC voltage. So, this corresponds to P equal to 2. So, we can improve upon this. See the next, okay, let me just go to a slightly complicated circuit. Suppose I want to further improve. What I do is I take 3 voltage sources and 3 thyristors. Connect each such circuit like this. So, there is in each circuit there is a thyristor in series with a voltage source. So, there are 3 such circuits connected in parallel. Let the instantaneous voltage here be Em cos omega ot. Now, these two voltages will have the same peak value, but different phase angle. Now, I mean, I did not get into how to get the phase angle. In the previous case, we said the phase angle is 180 degrees with respect to the previous voltage. Now, that is something based on your experience in an undergraduate course, maybe in a power electronic course, you are able to say that. Okay. So, similarly, I presume you should be able to say what should be the phase angle of this second voltage source. So, I can actually say that this should be shifted with respect to the first voltage source by pi by 2, 3 pi by 2, 2 pi by 3. So, if you okay, maybe the previous circuit may give some hint. Pi by 2, 120. Okay, here the difference is 180. Difference is 180. Now, how did we get that 180? It is not 360 divided by the number of such circuits in parallel. So, it is plus 180 here. Say plus 180 or minus 180, one and the same. Say even if I make it minus pi, it is one and the same. I mean, both are one and the same. Okay. So, here the phase shift should be 360 divided by number of such circuits is 3. So, it is 120. So, it should be minus 2 pi by 3, and this one should be Em cos omega ot. Say I have written minus 2 pi by 3 here. What should be written here? Minus 4 pi by 3. So, in this case, what is the pulse number? 3. So, the pulse number, as I said, is defined as the number of pulsations of the DC voltage in one cycle of the AC voltage. Now, it is also the number of pulses that are in total given to the entire circuit for the thyristors. So, if there is only one thyristor, I give only one pulse per cycle, okay, because there is only one thyristor. If there are 2 thyristors, there are 2 pulses to the 2 thyristors. Similarly, if there are 3 thyristors, there are 3 pulses, the gate pulses I am talking about. I am talking about the gate pulses that are here. So, each thyristor is assumed to be turned on only once. Yeah. Another point is to be noted. See, these waveforms which are drawn, the waveform of Vd as a function of omega ot is assuming that the gate currents are continuously given. Now, the purpose of having a thyristor is to get some control. I presume you are all familiar with the idea of changing the average value of Vd by changing the instant at which the thyristor is turned on. So, that is the idea. So, though I have drawn the waveform for the simplest case of continuous gate current, by changing the instant of gate pulse, one can get a different VD which has a different average value of VD in fact. Okay. So what we will try to do is, we will try to see how this can be generalized. So, in general, we can in fact say that there are many number of such circuits in parallel. So, what is the idea? The idea is very simple. Start with the most obvious circuit and see how to improve this circuit in order to get a DC side voltage which is close to the desired waveform, that is a constant value. Okay. So, for that we added one similar circuit in parallel, in fact an identical circuit, and in this case we have 3 such circuits in parallel. So, the DC side voltage is Vd, which is the voltage across these 2 terminals. Now, what I am going to show is, instead of saying P is equal to 2 or P is equal to 3 or P is equal to 4 so on, I will just draw a very general circuit where I have q such circuits in parallel. So, let me try to show a very general circuit now. So, the voltage here is Em cos omega ot. So, I will come to this voltage, but what I am showing now is a very general circuit where, suppose this is the first circuit consisting of a voltage source and a thyristor, this is the second circuit consisting of a voltage source and the thyristor, and so on up to the last circuit, which is the qth circuit. Say I denote the positive integer which corresponds to the number of such circuits is as q. So, for a general number of such identical circuits except for the phase shift, see they are identical except for the phase shift of the voltage. Okay. The peak value of the voltages are same. So, the peak value of the 2 voltage sources shown here other than the first one is also Em. So, what is the expression for the voltage across the second voltage source? Of course, it has a peak value Em cos omega ot minus, what is the phase angle? 2 pi by q. Okay. Now, coming to the last one, the last voltage source, that is the qth. I am not showing the third, fourth and so on. Okay. So, q is some positive integer. So, this is Em cos omega ot minus, what is the phase angle? 2 pi by q into q minus 1. Right. So, if I take out these 2 terminals, these are the positive and negative terminals of the DC side. The voltage across the DC side is Vd. Now, the question is, if you take a circuit like this, at any instant, how many thyristors conduct? Now, for the sake of simplifying the analysis, suppose I assume that all these thyristors act as diodes if I give continuous gate current. Okay. So, assume that, okay, for the time being, assume that these are acting as diodes. If I give constant, of course, see a thyristor is nothing but a diode if I give a constant gate current. Suppose, for the sake of simplifying the analysis, I do that. How many thyristors are conducting at any instant? Only one. Is that obvious? Is that obvious or not? Yes or no? Yes. Some people are saying No. No. It's obvious? Yeah. If it's not, let me know. Say, it's very easy to understand. Suppose I have two diodes, okay. Suppose I have 10 volts, 20 volts. So, this is say diode D1, this is diode D2. So, which diode conducts? Now, of course, I mean it is very difficult to say from this circuits. I should also show the DC side. Suppose there is a current flow possible here, I connect something on the DC side. Okay. So, if I connect something on the DC side and if some current, I mean of course, both are DC sides. For the sake of simplicity, I took instead of AC, DC voltages. Suppose I connect something across these two terminals. Okay. Some load is connected here, say a resistor. Okay. So, if some current flows here, I, then whether D1 conducts or D2 conducts or both conduct or none of D2 conducts. D2 conducts because both diodes are at, I mean the cathodes of both diodes are at the same potential, whereas the anode of D2 is at a higher potential. So, it is forward biased. So, once D2 conducts, the diode D1 is actually reverse biased. So, the potential of the anode with respect to cathode of D1 is minus 10 volts. So, it is a negative voltage which is appearing across D1 because D2 is conducting. So, that is why D1 conducts, D2 conducts. So, similarly, one can try to explain for the case of multiple circuits which are connected in parallel. So, that is what is happening in the case which I have shown above. So, there are q such circuits. So, the voltages are actually variables, they are sinusoidal. Okay. So, the at any instant the thyristor whose anode is at the highest potential conducts, all the cathodes are at the same potential. Okay. So, assuming that I have continuous gate current, I can, I mean for the sake of simplicity, I can take diode operation by giving continuous gate current. So, the point is at any instant only one thyristor conducts. So, we give a name for this particular circuit, this circuit which has q such combinations of a thyristor and a voltage source, we call this as basic commutation group. This is just a name, basic commutation group. So, the idea is try to get or build a circuit which has a waveform on the DC side close to the desired waveform, that is a constant value. Okay. So, what we do is we try to connect such basic commutation groups, many such basic commutation groups in parallel and series. So, suppose I take many such basic commutation groups in series and many such series combinations in parallel, I get a very general converter. So, that is how I build the converter. So, the intention is to actually get a waveform close to the DC side by having a very large value of what is known as pulse number. Now, I am not using the same notation which I used earlier. Say P was the notation used for pulse number. Here I am using a notation Q for the number of thyristors which are there in a basic commutation group. Now, I reserve the notation P for pulse number, which is the total number of thyristors or the total number of voltage sources which are there. So, if I have many such basic commutation groups in series and many such series combinations in parallel, so the total number is actually the pulse number. Now, the idea here is no two voltages will have the same phase angle, that is the idea. So, I mean the purpose of having different phase angles is I want to reduce the pulsations, say I want to get a waveform which is close to DC. So, if I have many such basic commutation groups in series and many such series combinations in parallel, there are so many number of voltage sources. So, it is actually equal to Q into number of such things in series into number of such things in parallel. So, there are so many voltage sources, each one is at having a different phase angle. So, the total phase angle is obtained by the ratio of 360 degree divided by the pulse number. Okay. So, the pulse number is nothing but the total number of such voltage sources or thyristors that I have. Okay. So, that is the idea. So, now in practice, how do we get these voltage sources? So, I mean, though for the sake of simplifying the explanation, I have shown as voltage sources. In practice, we get voltage sources as induced EMFs across the transformer windings. So, the practical circuit is something like this. I have a thyristor connected in series with a transformer winding. So, there are q such transformer windings. So, this is first winding, this is second winding, this is qth winding, and here I have the DC side voltage Vd. So, this is the circuit of basic commutation group. Now, one point to note is that in the practical circuit of the converter that is used at the transmission level, we can't just use one thyristor in any of these circuits. What we do is we use a series of thyristors to get the required voltage rating. Of course, we do not need parallel connection for the sake of getting the current rating. So, in the last class I mentioned that there was a time when we had to connect many thyristor devices, individual thyristor devices in parallel to get the current rating, and many such connections in series to get the required voltage rating. Now, the current rating is actually available. So, we have thyristors for the required current rating, but we do not have thyristors of the required voltage rating. So, when we connect many thyristor devices in series to get the required voltage rating, I will not show the individual devices. So, I will still use the same symbol. See, if I use this symbol which is for the thyristor, individual thyristor device, I will still use this even for the series connection of many such things. So, if I mean, so I gave I mentioned about this term thyristor valve. So, even for the thyristor valve, I use the same symbol which is used for thyristor device. Okay. So, I will not be showing multiple thyristors in series to show a thyristor valve. I will just again use the same symbol. Okay. So, in all the circuits I have drawn, the symbols actually mean thyristor valves, though it is it is the same symbol as that of the individual thyristor device. Okay. So, what I will do is try to build a very general circuit. So, from the basic commutation group I get a very general circuit of the converter. So, I just represent one basic commutation group by a box, and I connect many such identical basic commutation groups except for the phase shift of the voltage in series. So, this is having many such basic commutation groups connected in series. Say, connecting in series means the terminal which is marked as plus here is connected to the terminal marked minus of another commutation group. Similarly, the terminal marked minus here is connected to the terminal marked plus of the next basic commutation groups. Okay. So, connecting in series actually means connecting in series at the DC side, at the DC. Say, the DC side is very obvious here. Okay. There are so many AC sides. I mean, there are so many AC side, there are so many AC voltages or so many AC side terminals, but the DC side is unique. There are only two terminals corresponding to DC side. So, connecting in series essentially means connecting in series on the DC side. So, I get so many basic commutation groups connected in series. Now, I take an identical series combination and connect it in parallel with the previous one. So, I have shown two such series combinations of basic commutation groups. Now, what I do is I take many such identical series combinations except for the voltage phase shift and connect them in parallel. So, each box which I am showing here is a basic commutation group. So, there are Q thyristors and Q transformer windings in each of these boxes. And finally, I call these two terminals as the DC side terminals and the voltage across this is VD. Okay. So, what I am trying to say is, in each series connection there are S number of basic commutation groups. So, there are S basic commutation groups connected in series. Similarly, I have 1, 2 and so on up to R such series combinations in parallel. So, I am using the notation S for the number of commutation groups connected in series, and I am using the notation R for the number of such series combinations. Okay. So, in each of these boxes, of course, there are Q thyristors, Q transformer windings. So, the pulse number that we get P is the product of Q, S, R. So, P is actually the total number of transformer windings, the total number of thyristors. So, what I am trying to say is we get a very general converter circuit in this fashion. See, we started with a very simple circuit, and in an attempt to make the DC side voltage as close to the ideal waveform, we arrived at this. Now, the question is how to choose the value of Q, value of R, value of S. Is there any choice? I mean, some values are better than others. Of course, a larger value is good, but for a given value of P, are there some values of Q, R and S which are better than others in some way? Okay. So, that is what one has to do. So, what we will try to do now is do the selection of Q, R and S for a given value of P, and in fact, in the process we will also select P. I mean, we will also get some restrictions on P. So, for that purpose we define some figure of merit. See, this figure of merit is something which will help us in arriving at the values of Q, S, R and P as well. Okay. So, let me move on to two figures of merit that will be defined now. It should help us in deciding the values of Q, R, S. So, you can note down that R is the number of parallel paths, and of course, S is the number of basic commutation groups connected in series. Okay, that is the notation. S and R are just notations for these quantities. Okay. Now, in any circuit, what we expect is there is maximum utilization. We want the utilization to be maximum. Say, if we use a component and if it is not utilized, then we are unnecessarily investing. So, what helps us in deciding these values are the utilization. So, the utilization figures of merit will help us in deciding these values. So, we actually define two utilization factors. So, the first utilization factor is the valve utilization factor. So, abbreviated as VUF. So, for this I need a few more definitions. I need one of the valve ratings, say. So, I am using the valve without say normally the full term is thyristor valve. So, as I said, thyristor valve is nothing but a series combination of individual thyristor devices. So, one of the valve ratings is the peak inverse voltage. See, the peak inverse voltage is the one which actually appears as a voltage of the cathode with respect to the anode, the peak inverse voltage, PIV. Now, if you look at a basic commutation group, okay, let me go back to the basic commutation group. So, I mean, this particular figure also says what is the expression for the individual voltage sources. So, what is the peak inverse voltage? If you take any thyristor, all thyristors are subjected of course to the same peak inverse voltage, because all the voltages are having a peak value EM, same voltage, and there is uniform phase shift between the voltage sources. So, what is the peak value of the voltage that appears across any thyristor? Huh? EM, 2 EM. Any other answer? EM is 1, 2 EM. Okay, if it's a bit difficult to answer, let us take some example. Say, in order to solve the problem, better to go, I mean, if it is difficult, go from special case to the general case. I mean, trying to directly solve the general case may be a bit tough. Okay, let me take the simplest special case is 2 voltage sources. Again, I am going back to the voltage source just for the sake of explanation. In practice, it is a transformer winding. So, suppose I have a thyristor and a voltage source and another thyristor voltage source. This is just a special case where Q is equal to 2. So, this is a special case of Q equal to 2. So, in this case, it is EM cos omega OT, and this is EM cos omega OT minus pi. Now, what is the maximum possible voltage that can appear across the thyristor? See, at any instant one of the thyristors is conducting. Suppose, let me call this as T1, suppose this is T2. See, the voltage across the thyristor is not a constant. They are, I mean, because the voltages which are appearing here are sinusoidal. So, the maximum voltage that appears across any of these thyristors when the other thyristor is conducting is 2 EM. It is 2 EM. So, here peak inverse voltage is very obvious, 2 EM. But this is just the answer for Q equal to 2. This is the answer for Q equal to 2. Now, suppose I take the next complicated case, slightly complicated, is Q equal to say 3. So, the voltage here is EM cos omega OT minus 4 pi by 3. This is the voltage of this. Now, what do you say? At any instant, one of the thyristors is conducting, is less than 2 EM. Do you see that it is not 2 EM? Say, if I try to draw the phasors, in this case, if one phasor in the case of Q equal to 2 is like this, suppose I take this as the phasor E1. So, I show a bar to indicate that it is a phasor. So, I show this phasor as E2. So, if this is E1, E2 is out of phase or at a phase angle of 180 degrees with respect to E1. Similarly, if I try to represent these voltages by phasors, say E1, E2, E3. So, if this is E1, this is E2, then this is E3. So, the angle between any two phasors is 120 degrees. So, this is 120 degrees, this is 120 degrees. Now, the peak value of the voltage between, say, what appears across thyristor is nothing but the difference between any of these two voltages. Say, we are talking about the peak inverse voltage across the thyristor, it is nothing but the difference between any two voltages. So, if you look at the case of Q equal to 3, the difference between any two voltages does not have a maximum value 2 em, it is less than 2 em. Okay. So, take the difference of the any two phasors E1, E2, E2, E3 or E1, E3. So, it is less than 2 em.